Hi guys, welcome to Science in 5. In this video we're going to discuss momentum and Newton's laws. Now there are three aspects surrounding momentum and Newton's laws that you need to know. Aspect 1 is to do with momentum and impulse. Aspect 2 is to do with conservation of momentum. And aspect 3 is to do with elastic and inelastic collisions. In this video, we will focus on momentum and impulse. Suppose we have two vehicles, a truck and a car, with different masses, both moving in the eastern direction at the same velocity. Which vehicle is easier to stop and why? Well, the answer is the car. And one could give three different reasons for why the car is the easier vehicle to stop. The first argument that can be provided is the inertia of the objects involved. The car has a smaller amount of inertia. And we know that the less inertia an object has, the easier it is to change its motion. The less mass an object has, the lower is its inertia. Inertia being the measure of the tendency of resistance to changes in motion of an object. So the car has a smaller mass, it will have a smaller inertia, and it will be easier to stop or change the velocity of the car. One could say the car has less momentum. We'll dig deeper into that. One could also say the car has less kinetic energy. Okay, but let's focus on the momentum of the object for now. The momentum of an object is defined as the product of mass and velocity of an object. By means of a formula, P equals mv. So we can easily calculate the momentum of the truck by multiplying the 10,000 times 10 to give us 100,000 kilograms meters per second east. We could also calculate the momentum of the car by multiplying its mass and its velocity to give us 12,000 kilograms meters per second east. Momentum is a vector quantity, so its direction is also of paramount importance in its analysis. So we can easily see that the momentum of the truck is much larger than the momentum of the car. Hence, the car is easier to stop because it has a smaller momentum. Well, we'll talk about momentum and impulse and hopefully that argument about why an object with a smaller amount of momentum is easier to stop. What will cause the momentum of an object to change? The change in momentum is given the symbol delta P. Well, let's go back to the formula. P is equal to mv. So this means for momentum to change, we can change the mass of the object. Or we can change the velocity of the object. But you'll notice that most of our examples will focus on the change in velocity of the object. According to Newton's first law of motion, if there is no net force that acts on an object, its velocity remains constant. Consequently, if the mass is also constant, then the momentum of the object will remain constant. A net force will cause a change in velocity, which will also cause a change in the momentum of an object. Well, the net force can be calculated by saying mass times acceleration. But the acceleration quantity itself can be broken down into the rate at which velocity changes. So mass times velocity gives us momentum. What of mass times the rate of change of velocity? Well, this will still give us F net, the net force. So there are two ways of looking at the net force. One way is to say it's the mass times acceleration, or it is to say it is the rate of change of momentum of an object. From this last formula, if we multiply the left-hand side with delta t, we get F net delta t. The right-hand side, the delta t cancels out, will remain with mvf minus mvi. The quantity mvf represents final momentum. The quantity mvi represents initial momentum. Final momentum minus initial momentum will give us the quantity change in momentum. The quantity F net delta t is given a special symbol J. And we say J is equal to delta P, where J represents the impulse of an object. So impulse J is equal to change in momentum. There are two definitions of impulse. One, we could say the impulse is the product of net force and contact time. Or we could simply say the impulse is the change in momentum. As a result, we can have two units for impulse. One is the Newton second, based on the formula F net delta t. The other, the kilograms meters per second. Impulse is a vector quantity and it has a direction too. For calculation purposes, impulse is equal to change in momentum. This can also be referred to the impulse momentum theorem. So, to calculate the impulse of an object, two options. Option 1, use F net delta t if F net and delta t are given, or simply calculate the change in the momentum of an object. Now, we can represent momentum and impulse using vector diagrams. The first thing we need to know is to use this formula that says delta P is equal to PF minus PI, which simply means final momentum minus initial momentum. Suppose an object has momentum of 10 kilograms meters per second in the eastern direction, and then a change in momentum occurs, delta P. But we already know that delta P is the same as impulse. Okay? So this object receives an impulse of 15 kilograms meters per second in the eastern direction. What will be the final momentum? If we go back to this equation that says delta P equals final momentum minus initial momentum, we can easily arrange and say final momentum is the impulse plus initial momentum. We can simply swap the left-hand side and the right-hand side like that. So final momentum equals delta P plus initial momentum. So if we take east as positive direction, initial momentum is positive, the impulse is also in the eastern direction, therefore the impulse is also positive. So this means that the final momentum of this object will be 25 kilograms meters per second in the eastern direction. Another example, another object with initial momentum 10 kilograms meters per second. receives an impulse in the opposite direction. This could be a retarding force opposing the motion of the object. What will the final momentum be? Well, we know that if we take the east as positive, we can use the formula final momentum is impulse plus initial momentum. Or final momentum is change in momentum plus initial momentum. In this case, the change is in the opposite direction of initial motion. The impulse is thus negative. So when we apply the formula, it's going to be minus 15 plus 10 to give us a change, a final momentum rather, of minus 5 kilograms meters per second. But the negative simply means the final momentum of this object is in the west direction. So the final momentum of the object will be 5 kilograms meters per second in the western direction. So impulse equals change in momentum, or F net times delta t. Given a force versus time graph, the impulse becomes the area under the graph. So impulse equals the area under the graph. Here's an example. An object of mass 200 kilograms is traveling at 5 meters per second east. The force versus time graph below shows how the net force that acts on the object changes with time. Question 1 says, calculate the impulse delivered on the object in 10 seconds. Question 2, show that the object reaches a velocity of 9.5 meters per second after 10 seconds. Question 3, calculate the velocity of the object after 20 seconds. So let's go. To calculate the impulse in 10 seconds, this is a force versus time graph. We're going to say impulse is equal to the area under the graph. Now, if you look at the graph for the first 10 seconds, you've got two shapes. The first shape, A, is a rectangle. Second shape, B, is a triangle. So you should be able to say, well, what are the dimensions of those two shapes? This is 100 by 8 rectangle. And this triangle is also going to be 100 this side by 2 this side. Area of a rectangle is length times breadth, triangle half base times height. Since both of these are positive, or the area is in a positive range, the impulse should also be positive. A total impulse is 900 kilograms meters per second in the eastern direction. Show that the object reaches a velocity of 9.5 meters per second after 10 seconds. Well, oh yes, the impulse is also 900 newtons seconds east. Remember, impulse is 2 units. We're going to use the formula delta P equals PF minus PI, or impulse equals final momentum minus initial momentum. We've already calculated the impulse, which is 900 kilograms meters per second. We substitute into that formula. What we are interested in is the final velocity. Now it's an issue of playing around with the maths. We get 1900 is 200 VF. Divide both sides by 200, you get the final velocity is 9.5 meters per second. It's going to be in the eastern direction. Question 3 says, calculate the velocity of the object after 20 seconds. Well, we'll need now the total impulse, the total area under the graph. Okay? So one option is to say, what is the total area under the graph for the entire 20 seconds? So we've got A, B, and we can now introduce another region, C. What is the combined area of A, B, and C? Note that here, since we have got a negative force after 10 seconds, the impulse after 10 seconds must also be negative. We must add that as well. So, length times breadth for region A, region B, triangle, region C, also a triangle. Guys, be careful of the values there. Don't be confused by those values. Remember, in region C, this length here is actually 10. And this is actually 300 or negative 300. Okay. Once we get that, then it's fine. It means we are now ready. The total impulse delivered on this object in 20 seconds is negative 600 Newton seconds. Once I know the total impulse and the initial velocity, I can now work out the final velocity of the object by saying impulse is change in momentum. Negative 600 is now 200 Vf minus 200 times 5. I get 400 equals 200 Vf. Therefore, the final velocity is now 2 meters per second east. Okay. Alternatively, I could use another technique. I could say, instead of calculating the impulse for the entire region, I could calculate the impulse only for C. Why am I doing that? Because I know that here the velocity is 9,5. So the impulse for C is going to be a half base times height, which is a half of 10 times the negative 300. Okay. 10 times negative 300 is negative 3,000. Half of negative 3,000 gives me negative 1,500 Newton seconds. So, I can now work out, since I know the impulse here, I can now work out the final velocity here. I'm going to use the same formula and say delta P equals final momentum, which is mvf. Delta P is mvf minus mvi. The delta P is negative 1,500. mvf, I don't know what the final velocity is, so I'll write it as 200 vf minus 200 times 9,5. If I solve this simple equation again, I'll discover that once I take the 200 times 9,5, this side it comes positive. I'll end up with the same, 400 equals 200 Vf, therefore Vf equals 2. So in this case, you could have used that reference point again, where you start by looking at the velocity of the object at 10 seconds. And the velocity was 9,5 meters per second. And then you can work out the final velocity after 20 seconds. So, impulse equals area under graph when given a force versus time. Impulse and safety. To stop an object, a force is needed. This is the force of impact. So in the case where an object collides with another object, the force that stops that object, we call it the force of impact, different from a braking force. Okay, so force of impact is often supplied by barriers, for example, a tree, a wall, or another object. So when an object collides into that barrier, the barrier exerts a large force of impact to stop the object. This force is transmitted to the passengers inside a moving vehicle. Okay, and it poses a risk of injury. How to reduce the force of impact? Well, we'll need to use the impulse momentum theorem. F net times delta t is equal to delta p. Suppose we have a car with an initial momentum of 12,000 kilograms meters per second that is brought to stop by a barrier, and its final momentum is now 0. We can easily calculate the change in momentum of this car by saying final momentum minus initial momentum. 0 minus 12,000 to give us negative 12,000 kilograms meters per second. The negative just tells us that in our example, the car is moving east. The impulse that stops the car must be west. Now, the magnitude of the change in momentum will remain the same irrespective of how long it takes the object to actually stop. Whether the object stops in 3 seconds, 5 seconds, 2 seconds, the delta P value will remain 12,000 in this case. So, the quantity that becomes of paramount importance is the collision time, the delta T. And that delta T will ultimately then affect the size of the net force. Okay, let's investigate a little bit. Keep this value of 12,000, we're going to use it. So we can rearrange the impulse momentum theory formula and say the net force is actually equal to the rate at which momentum changes. The quantity delta P over delta T is the rate at which momentum changes. So we're going to plot graphs of contact time and force of impact using the car example. We know that our change in momentum was 12,000. The magnitude was 12,000. We're going to deal with that. Okay, so it's 12,000. So the net force will be 12,000 divided by delta T. Okay, so let's roll. If the contact time is 0.25 seconds, the net force that will be experienced by the passengers inside will be 48,000 newtons. So if I go to my graph, 0.25 and 48 is there. Just take note that on the y-axis, you can see that it says force net times 10 to the power of 3 times 1,000. So it's 48,000 newtons. So there's my first point. What if the time is 0.5? We have doubled the collision time. What happens to the force of impact? The force of impact becomes half of the previous value. The previous value was 48,000. Now the new value is 24,000. If the collision time is now 0.75 seconds, what is the force of impact going to be? It's now dropped further to 16,000 newtons. So 0.75 and 16,000, it's going to be somewhere there. And then finally, what would happen if the collision time became 1 second? The force of impact drops again to 12,000. So 1 and 12,000 there. So we can actually join these points to form this kind of graph. An inverse graph. So we can clearly see that as we continue to increase the contact time during the collision, the force of impact keeps dropping. So we can actually say the net force or the force of impact is inversely proportional to the collision time. And this is very important for safety considerations. If you can increase the collision time during a collision, then the force of impact will be dropped significantly. In the case of bouncing an object, impulses are greater when the object bounces. So when you land on a rigid object, you bounce off. And that is why the risk of injury is much greater, because the rigid object makes you bounce off its surface, and it takes an additional impulse to stop an object and send it back in the opposite direction than it does to simply stop the object. So this is why it is not safe to do sports like high jump and land on concrete surfaces, because the concrete surface will bounce you off its surface, will stop you and send you in the opposite direction. So the additional impulse is supplied by the surface on which the object bounces. So in the case of vehicles, we don't want vehicles to bounce off each other. In the case of catching a fast-moving ball as a cricketer, you don't want the ball to bounce off your hand. Okay, because that will mean that the risk of injury becomes greater. Why does a cricketer move their hands back when catching a fast-moving ball? Why is a soft cushion like thick mat used in high jump as opposed to using a rigid object like a desk? Why does one bend their knees when jumping from a wall? It's all to do with the contact time. You're trying basically to increase the contact time and reduce the force of impact. So we have said that the force of impact is inversely proportional to the contact time, or the contact time is inversely proportional to the force of impact. So for example, by pulling his hands back, a cricketer increases contact time to stop the ball. This makes the catching the ball safer and minimizes risk of injury. So it's about contact time. In the case of cars, what can we do to make collisions much safer? We have realized that cushioning a collision is very important, but we can't put a cushion in the front of a car. What can we do is to design a region called a crumple zone. So these regions are designed in the front of a car, designed to crumple upon impact. This increases the contact time of impact and reduces the force of impact transferred to the passenger. So you can generally hear people say, oh, the cars of today, they're not as strong as the olden cars. A small accident in the front of the car seems to crumble or seems to fold. It's by design. That folding part or the folding aspect of the car during a collision is to increase the contact time so that the force of impact becomes less. In the case of an airbag, how does an airbag contribute to safety? The airbag acts like a cushion, allows you to sink in. This increases the time it takes to stop you and reduces the force of impact. So instead of just going straight into the dashboard of the car or the steering wheel of the car, the airbag cushions. And that cushioning effect means you take a longer time to stop. And as a result, the force of impact is greatly reduced.